This is an introduction to probability based upon Chapter 4 of Triola's book and Brace and Brace's books. So I'm going to look at set theory in mathematics and compare it basically to what goes on in probability and statistics. So hopefully if you've had set theory before in math in some way, shape, or form, then you can relate that to your study of probability at this point. So the first thing that we encounter is a set. And a set in mathematics, of course, is just a collection of things. And in statistics, our set is an event, and it again will be a collection of things. And in math, those things that we deal with are called elements or members, and in statistics, those elements or members are called simple events. So when we talk about sets in mathematics, we talk about sets in two different ways. We'll talk about them in a roster form or in set builder form. We do the same thing in statistics. We have roster forms and we have set builder notation that we'll use. So just a little reminder about what those look like. A roster form is a list of events, just kind of like you would expect, like a roster of players on a sports team or something, and they start with braces. And braces, remember, are kind of the curly cues. They look like this. And the roster form then lists the elements or the members or the simple events in the outcome as outcomes, and then it ends the set with the brace. And a set builder notation also starts out with braces, but then it says, okay, we're going to describe a variable. And in statistics, when we describe variables, we call those random variables rather than just a variable. And then it goes with this straight line, and that straight line up in vertical line is called such that. So when you see that notation, it says, okay, here's the variable I'm describing, and this is what it means. So x such that, and then it describes what x means. Now, sometimes that can be a verbal description. Sometimes if it's in math, especially, we'll use less thans, greater thans, etc. So those are some of the ways that we can describe sets of numbers, sets of simple events, etc. And then we end again with a brace. So some of my examples here is the vowels in the English letter. So in roster form, we would put a brace and then we'd list A, E, I, O, U. If we were going to do that in set builder notation, we'd say X, such that X is a vowel, and that way it leaves a little bit more to the imagination as far as what we're talking about, and it's not as descriptive. But as we know from our study of mathematics, not all sets can be described by a list. Sometimes we just have to describe them because they're so infinite in their numbers, there's no way to list everything out. The next one that I have here is as an example, the outcomes of a roll of a single die. So if I roll a single six-sided die, I get a 1, a 2, a 3, a 4, or a 5. So that would be the roster of that. Now if I wanted to describe that, that would be x, such that x is a whole number. So this funny looking thing that looks like an E is actually a Greek letter. It's epsilon. In math and science we use epsilon to mean an element of. So we already discussed what an element is. So an element of, and then I describe it using some mathematical notation here. X is a number between 1 and 6, and the equal sign means inclusively. So if we're only talking about whole numbers between 1 and 6 inclusively, we're talking about 1, 2, 3, 4, 5, and 6. Now the third one is the outcomes of a roll of a pair of die. So if I have a red die and a green die, these are all the possible outcomes. I can get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. And that is the first number being from the red and the second number being from the green. Sometimes it just helps to imagine the red and the green, because then when we go and see the 6 and the 1 down here, we don't get confused and go, well, we had a 1 and a 6 paired already. Well, that was a 1 on the green die and a red getting a 6, whereas this is the green gets a 6 and the red gets a 1, which are obviously then totally separate simple events occurring. Now, the other way to do it is, of course, to do it in set builder, and then we say, okay, we're going to get ordered pairs with x's and y's such that x and y's are elements of the 1 through 6. And of course, this makes the reader have to come up with all of these 36 possible outcomes, which can be kind of a little tricky if you're not really sure how these simple events are being built. So that's where the roster form is better, of course. Now, the next thing we're going to do is we're going to um, name the sets using capital letters, just like we did in math. We're going to name them with a capital letter here, A. And so A is equal to X's, such that X is a vowel. And then we can start talking about subsets, and subsets are also important because we know that we have smaller sets that are made up of the larger set's elements, and that can happen in statistics too. So we can have different events that are described based upon the same basic universe, and then but the sets will look different. So when we talk about a subset, one of the notations we see for subsets looks like A is a subset of B, or A is contained within B, as it's written over here. When that symbol is backwards, it looks like a backwards C. That's the contained within. That's not a very normal notation. It's much more often read like this and using the subset. Now, sometimes the subset notation also has an line underneath it, like a equal sign almost, and they both mean essentially the same thing. So A is a vowel, A is X such that X is a vowel, and B is X such that X is equal to A, B, C, D, E, so on and so forth, meaning, of course, the ellipsis meaning and so on and so forth. The ellipsis, by the way, is the 3 dots here. So what we're talking about are the vowels of the English alphabet and then the English alphabet over here. So A is contained within B, therefore A is a subset of B. So one of the things that we should know about subsets is that when you have a set that is contained within another, and that set in turn is contained within the first one, then you have two equal sets. So if we describe A as the set of vowels and C as A, E, I, O, and U, those are exactly the same sets, right? So A is a subset of C, and C is a subset of A, and when that's the case, then A and C are equivalent to one another. So another important note to come out of that is that a set is always a subset of itself. The entire set itself is a subset. So that was something we studied in math as well. Now, I had mentioned just a little bit ago about a universe, and a universe is, in statistics, everything that we're drawing from. So when I talk about numbers, most typically we talk about the set of real numbers until we get into the end of intermediate algebra, where we introduce the complex numbers. But for the most part, the real numbers are the set of numbers that are defining universe. And in statistics, our defining universe happens to be called the sample space. So universes and sample spaces are the things that are similar there. So let's just write that down so that we get that idea. So a sample space, and that in statistics is what we call our universe. Sorry, I wrote it backwards. So sample space, let me put this in parentheses, and then this in mathematics is our universe. And our universe, or our sample space, when we write those in math, we usually write kind of a scripty U for the universe. And it's no different in statistics. We usually use kind of a scripty S to define the sample space, which again is our universe. So another thing that we need to remember from our study of mathematics is what a null set or an empty set is. And a null or empty set, we can say that those are things that contain absolutely no outcomes, right? No simple events, no possibilities in them. And these things would be symbolized this way. This is another way that we symbolize them. Sometimes you'll see this as more of a one off to the side, either or. Sometimes this one will have lines on the top of it because it looks like a Greek letter. But these are the two main ways that you see them. And you do not combine them. You don't put this symbol within the braces, because then it's no longer an empty set. It has something in it. So it's kind of confusing sometimes, the fact that an empty set actually can be described but still be an empty set. So here's an example of a set that's an empty set. If we're considering our universe to be all real numbers, which set builder notation in mathematics, if you do not state any other set of numbers to be drawn from, you are assumed to be under the real numbers in set builder notation. So g is described as x such that x squared is equal to -1. Well, we know in the real number system there is no such thing as anything being squared giving you a negative number. And so this set, even though it's very well defined here, it just doesn't exist under the set of real numbers. Now that number exists, of course, under the complex numbers. So if we were to change the universe here, we could certainly have a defined set. But at this point in time, defined under the set of real numbers, this is definitely a null set. Another example of this would be if we let all of our universe be all the months with 31 days, and we define G as February. Well, we all know that that February is a month, right? So we're talking about months, and it's absolutely valid to say. However, as soon as you say, well, our universe is 31-day months, we know that that doesn't exist as far as February is concerned. So February is indeed a null set underneath that universe. So just a little reminder here about something called a Venn diagram. So Venn diagrams, remember, help us to show things visually in set theory. So we have a rectangle that represents our universe. So this rectangle in math a lot of times represents the real numbers. And then the circles here, they represent the sets. And when we see one circle overlapping another, this little shape in the middle that looks kind of like an eye, that's the intersection of those sets. If we want to describe something that is a subset of another set, we draw the circle totally within it, like this C drawn totally within B. And then if we take a look at A and C are two sets which we call disjoint sets or mutually exclusive, because there's absolutely no touching or overlapping of these two circles. That means that everything that is in C is exclusive of everything that's in A. In other words, there are no elements that are the same. Whereas with A and B, we have elements right here within this overlap that are the same, and that is, of course, what we mean when we say intersection. So let's go ahead and write down some symbols here so you remember, because I will use these symbols when I talk about statistics and I talk about the probabilities of things. So if I say A intersects B, this is the intersection of the two sets. And intersection means the overlap, what things belong to both sets at the same time. So in terms of a Venn diagram, if these are my sets A and B here, then the overlap of these two sets is this little bit right in here. So that is what we mean by the intersection of those two. And then another thing that we talk about in set theory is we talk about the union of two sets, A union B. Now, A union B is just simply the collection of everything in the two sets. So if I'm talking about A union B here, like this, then what I'm talking about is I'm talking about everything within the bounds of these two. So I like to show this by traveling around the outside edge, and you see that captures everything in here. And even though this little eye-shaped piece would be in both of them, I don't say it twice. I just say it, you know, that it's in there, right? Once I've got it, I've got it. And then let's go back to the A intersect C as being a null set, this meaning that they're mutually exclusive sets. And that means that we have no overlap whatsoever. So this is A and this is C. And that's where I'm going to end for now, and we'll come back and we'll get a couple more examples of that in the next little video.